I want to start by giving a little bit of background. When you think about 50 years of NERSC history, and 50 years, if you go back that far and a little bit further, there's in fact a very interesting common origin between what we do at General Atomics and the NERSC activities. And it's worth going over elements of this because I think understanding common origins is very helpful in thinking about the future as well. So General Atomics was founded in 1955 to develop the peaceful use of atomic energy located in San Diego. When you look back at the history, those years in the late 50s, following the Eisenhower's Atoms for Peace initiative and Geneva Conference, was a remarkable creative period for science and also for nuclear energy. So, and almost immediately after that conference, General Atomics was kicked off with a conference in San Diego in 1956. And the oral history of those days and the excitement around deploying peaceful uses of atomic energy is very clear in the oral history provided by Freeman Dyson. It's readily available on YouTube. So soon after that event, we developed what's called the trigger reactor, which is actually still in use today. In those days, things moved very fast. So within 2 years, there was a training reactor that was quite successful, distributed around the world, 68 of them. And they're actually still in use today. And if you go to Irvine or Columbia and ask if you can find that, they'll show you where it is. And so the importance of this is at about the same time, fusion started emerging. And of course, if you think about the peaceful use of atomic energy, it was natural at that time to ask if we could also harness and control fusion energy. So at that time, General Atomics started looking at fusion. And the leader for that is a remarkable creative individual, Tahira Wakawa. And his work led to what is now the D3D National Fusion Facility, which is the key facility that the Department of Energy operates, the GA operates for the Department of Energy, and is the primary experimental facility for fusion energy research in the United States. And the interaction right now between the D3D program and NERSC is extremely strong. And we are entering a very exciting time for the future. And to give you a sense of that common past, Bruce Henderson gave a very good discussion of the early days before NERSC was called NERSC. It was called the Controlled Thermonuclear Research Compute Center, actually in Livermore, before it moved to Berkeley. This was the brainchild of Trivelpiece, who saw both the challenges of fusion and the differentiated computation from it. Very perceptive and insightful. And he brought on John Killeen, who at that time was the leading computational physicist in the fusion program, again at Livermore. And when we look back at the history of that day, there are elements, I believe, of NERSC culture that are inherited from that beginning. John's philosophy was to work very closely with experimental programs to provide timely input with calculations that could enable the experimentalists to decide what they should be doing next. And that may seem obvious, but it wasn't obvious in those days that you have such a tight coupling between computational physicists and experimentalists in the control room. And in fact, today, with the emergence of the integrated research infrastructure, the emergence of the high-performance data facility, the coming of the FAST program, the AI revolution, that coupling to experimentalists and physicists in the control room is coming back in full force. And we are greatly benefiting both from the culture of NERSC historically, which goes in many ways back to John Killeen, and the strengthening and understanding of the critical contribution that computation and data science in particular can make to experimental programs. But in the context of theory and calculation, one other element of this that I want to point out is, and unfortunately, I don't have enough time to discuss these discoveries in detail, but there were numerous, I would call numerical discoveries that led to fundamental shifts in our paradigm of emergent phenomena and collective phenomena in fusion plasmas. So there are various occasions where Killeen's, again, focus on really working closely with the experimentalists in the control room led to fundamental understandings that passed by the analytical theorists of the day, even of the likes of Rosenbluth, and created, again, new paradigms in the way we understand the emergent phenomena that controls transport and stability in fusion plasmas. So just to give you a sense, I would like to thank Dave Shizzle for finding this. We all know this wonderful diagram from ESNet 6. Thank you, Eli. If you go back to 1977, the diagram was much simpler. But you can see, again, coming out of this atoms for peace era, all this excitement around eventually harnessing and controlling thermonuclear fusion, how the initial network involved GA, PPPL, Los Alamos, and Livermore. So again, these were very exciting days. And the culture and role of NERSC at the time, again, was deeply embedded in the fusion program. Today, the state of computation has really leapt forward in remarkable ways. One of the keys in fusion simulation is to capture enough multi-scale interactions that you can identify emergent behavior that controls the macroscopic properties of fusion plasmas. And these are just two examples of gyrokinetic simulations of various forms to try to understand, on the left-hand side, the transport phenomena at the very edge of the confined to unconfined regions of plasma. On the right-hand side, these simulations are performed to understand the transport properties of the core plasma. But in each case, the challenge is to resolve, find enough detail at dissipation that you can extract the primary collective global behavior that controls the bulk plasma. And this kind of work, particularly with the advent of the SIDAC programs and the remarkably successful leadership class computing facilities, has really led again to dramatic progress in the field. And I would love to discuss more of this and how it has impacted the field. But I wanted to come back to experimental programs because during this period, I would say that experimentalists in control room have not taken advantage of high performance computing in the same way that the simulation scientists have taken advantage of in order to advance fundamental understanding. And there are various reasons for this. Much of what goes on in the control room today is quite recognizable to what went on at the turn of the century. The use of big data is both in terms of simulation data, calculations, and raw data, in terms of guiding, planning, and ultimately interpreting experiments and monitoring systems. It's really in its infancy. And there are reasons for that. But fundamentally, without the advent of machine learning methods, we found that these, the trade-offs, traditional trade-offs between model fidelity and latency made the application of such modeling for experiments rather challenging. And if we now look at why to advance our understanding, our application, theory modeling, and data science models, this is a very good reason. Although a great deal of scientific understanding has been achieved through simulation, we still confront major to scale fusion devices and understanding reactors. Fundamentally, a fusion plasma, achieving and sustaining a fusion plasma, is about negotiating multiple operational boundaries to optimize the trajectory of the plasma and the trajectory of the actuators and systems throughout the life of that discharge. Again, to avoid operational boundaries and to maximize performance. And this is an example of something called a disruption. And it is only one operational boundary. And it's a rather severe one. And what you can see here is the damage that can be done by running into this particular type of operational boundary that needs to be avoided. And the instabilities can grow so fast that you cannot really control them when they come up. And so you have to have intelligent systems that forecast far enough into the future the behavior in response to actuators to be able to affect the trajectory of the stable discharge to avoid these instabilities. And this is where really machine learning comes in. And recently there have been dramatic advances that indicate we have a real shot at overcoming the challenges, essentially multi-component stability boundary limitation and trajectory optimization. This is an example from a recent Nature article that a colleague of mine at Princeton University that shows the use of reinforcement learning in this space to maximize the plasma pressure, which is indicated by the black curve, while avoiding hazards. In this case, the red regions on the top are a stability boundary or an inferred or estimated stability boundary from data. And the cost function also weights against low pressure so that you balance the optimization of plasma performance for fusion with the minimization of triggering instabilities. And this is really, I think, a dramatic demonstration of a capability that we have dreamt of for a long time. And it shows the potential of machine learning. And we've only scratched the surface, but we see enough here that we have a straight shot of making dramatic improvements in control and optimization with these modern methods. Another example of this, if we must develop models that forecast far enough into the future that we can affect the discharge and actuated trajectory, then we need to convert theoretical models, advanced theoretical models into fast executing models, like surrogate models of gyrokinetic simulations. And there's rapid progress in this area as well. So the future looks very exciting. But to harness that future and to really leverage these capabilities, we need to act quickly. And the reasons are, one is that there are various factors that are coming into play to accelerate the development of fusion. The White House bold decadal vision for fusion was released in 2022, and it calls for realizing fusion energy on a decadal timeframe. The convergence of climate, energy security, and economic competitiveness issues, the surge in private investment in fusion, $7.2 billion raised in private equity over the last 4 years, the promise of AI through the leading indicators that I've indicated already, and the fact that ITER operations are coming in the 2030s, and these operational boundaries become more severe as we go to larger fusion scale, is really creating, again, this urgency to comprehensively deal with performance optimization and multiple operational boundary navigation in the next few years. And I would also say that the White House AI position paper and strategy from 2023 is also very helpful. And these two areas really converge, both for workforce development and for advancing fusion and for advancing US leadership in AI. So I think there's a terrific convergence here. So these initiatives there are 3 initiatives currently being pioneered on D3D in participation with FES and OSCA to accelerate data-driven solutions for fusion challenges. One, as I mentioned, is the integrated research infrastructure. We've had this terrific collaboration with NERSC, and we couldn't ask for better partners. The other is development of a fusion data platform, essentially to democratize. People like to say that, but it's true. It's to broaden and enable access, community access to the tools and capabilities for machine learning and AI, which is a very important strategic consideration for the United States in general. And the other is the development of digital twins and agents for orchestrating models and acting on the information coming in from the virtual and the physical. The integrated research infrastructure activity, in our case, started a couple of years ago, and it's really turned into something very successful, both in terms of what it achieved, but also how it illuminated the path forward and the vision for the future of fusion energy research through advanced computation and collaboration with OSCA. And the key thing to understand is, up until recently, fusion is really data rich but analysis poor. There are significant bottlenecks to detailed analysis, and so we looked very carefully at where the bottlenecks were, and it was clear. All obvious. Most good ideas are almost obvious in hindsight, right? But we had to dig into this, and we realized that the critical step of plasma state reconstruction was far too human in the loop and very heavy on individual physicist engagement to really enable high throughput analysis. And so when we started on this, we realized the plasma reconstruction challenge was the first thing to automate and then to accelerate and bring the reconstructed data into the control room. I'm very happy right now to report that from a historical average of about 0.1% of the D3D data being analyzed in detail, we can now essentially automate that to the point where we can deliver near 100% of data analysis, not just after the experiment, but while the experiment is being executed. This is a dramatic turnaround. And given that in machine learning and AI, data is the point of the realm, it's extremely important development because it opens up so many possibilities for us. The other aspect of this is, what do you do with the plasma state reconstruction? One of the first things that we decided to do was address facility protection. So there we have neutral beams that inject power into plasma. Those beams ionize. Some of those particles escape, they strike the wall. So what we said, and we know that running certain configurations can lead to damage, and we don't know a priori all the possible situations that can lead to damage. And that damage to the facility can bring the facility down. It can stop operations for weeks. So we said, okay, let's do this and see what the result is. See if we can anticipate failure modes or damage to the facility. And I'm glad to report that, in fact, during at the upcoming SC24 meeting, we'll be able to demonstrate this, where we actually run the IRI API and distribute workload for this during experimental operations to ALCF, NERSC, and OLCF, and get the results back into the control. And as a validation of this workflow for facility protection, we have this example, which is really very nice. On the right-hand side is a melt region that brought the facility down for 2 weeks. That has enormous scientific costs as well as financial costs. So using this procedure, we were able to reproduce essentially the melt mark that is telltale sign of how the break occurred and the particular configuration that was required to produce that break. So that validation gives us confidence. The next step is to integrate this modeling with the monitoring of the facility. The second element is a fusion data platform. And in order to be able to create access to the D3D, in this case, research community, to all the data in a form and the tools in a form that everyone can participate in AI and machine learning model development. Right now, we have some spectacular examples of success, but not everyone in the D3D team, not every collaborator, and not every institution has the resources to be able to pull the data and put it on a performant platform to enable them to do leading edge research. And again, if we look at the White House strategy for AI, calling for broadening access to data and tools, this is an absolute priority. And at least within the D3D program, we can address this. And so we were funded by DOE to do this. And it's really a pilot, but it's a pilot focused on developing a minimum viable product within a year of the start of the project that we will push out and gain experience and feedback from the community. I can discuss this further in detail if you like, but the key is that the project will be flexible and to coordinate with the IRI and HPDF communities, which will in long term be the key to our success. We're very excited by this, and we think that, and we're working also with Frank Worthwing at SDSC. It's a pleasure to work with. It's a wonderful set of characters there. And I think we will learn very rapidly what the community needs, and we will bring that forward and share that and work with you so that we can all learn together. The other is an obvious application to plant monitoring. I won't go into this, but just to say that traditional plant monitoring methods basically have such a high false positive rate that they push the monitoring application off to the side so that someone can handle all the flashing lights, and then they ignore it in the control room. So the idea is to get the false positive rate down, and we've succeeded in this one case as a trial using the platform to access the data from the facility and to develop using conditional normalizing flows, in this case, a model that dramatically decreases the false positive rate for anomaly detection on this power supply. So we think that we're on the right track here. And I would add that the objective of the Fusion Data Platform is to develop common standards for engineering, sensor, and physics data is also opening up lots of new possibilities. It's remarkable how the engineers and the physicists really communicate. And that's in fact reflected in the fact that the data standards are completely different. Even the coordinate systems are different. You'd be surprised. Where a difference can crop up, it will. And so I think that this will lead to advances when we bring these data sets together in a consistent, uniform way. And finally, digital twin. Now, digital twin can mean many different things to many people. The NASM report on digital twins distinguishes them from simulation by saying that there is bidirectional flow of information. So we think that report is very good, but I believe that the definition as presented is deficient, because without agents, whether they be AI or not, mediating that exchange of information, the exchange of information itself is not very meaningful. So our vision here is that the orchestration of essentially AI machine learning models and a digital twin with agents that probe both the digital and the physical and have certain authorities to do certain things on certain latency timescales is important. And as I mentioned earlier, the whole thing about fusion is anticipating and not just responding like a traditional control PID. So in order to do that, you really need models that simulate on a hierarchy of latencies. The shortest latency timescale is for direct real-time control of the facility and actuators. Then there are longer latency timescales that can forecast and advise and control in ways that need to be properly determined. A discharge, say a long pulse discharge, or if you have short discharges, you can plan the next pulse. And then there are longer operations. And this latency hierarchy also, in a sense, follows a fidelity hierarchy. You want a pipeline, as we discussed yesterday, that pushes models to lower and lower latency and to greater autonomous operation. But you're always going to have a development pipeline where you're developing new models, more sophisticated models, and you want to develop them on different levels. And so we really see that this digital twin concept will require integration, deep integration into IRI, HPDF. It will require necessarily edge computing, mesoscale, I would say, computing, and leadership class computing. And again, if you look at the IRI vision, it really does state that we need a data and computation ecosystem that goes from the edge to the leadership class centers. And you can understand why, particularly in the fusion context, where actual real-time control has to take place at the edge, but where you need this pipeline to develop the models and capabilities and to provide different fidelity analysis on different latencies. So finally, the visual realization of this is important. This is not, there is no agent here, but what we're doing is we're calculating the, in this case, the neutral for beam injection on ALCF and NERSC, bringing the results back to the control room, and then visualizing where the neutral beam particles strike the walls, and superimposing that on the as-built geometry with laser scans. We've learned an enormous amount just by doing this. This is an offline calculation. Our plan is to bring this to the control room and to have this tool in the hands of the operators. And again, this is only the very beginning of this process, but we're very excited. And again, the goal is to fully integrate these capabilities within IRI and to figure out how to illustrate all this. So I would like to say finally that really the history of the NERSC, I think from Adam's piece to the present day, demonstrates remarkable leadership. We would not have embarked on this journey if we hadn't picked up the phone and said, you know, NERSC folks, Debbie, Eli, what can we do here? We have challenges. We need to think out of the box. We need to work with the broader scientific community, and they were right on. Really, thank you for that. The legacy of NERSC really is deeply embedded in the culture and history fusion. The partnership again between D3D and NERSC, in my view, clearly is central to our emerging vision. And I think the future is actually extremely exciting. And if I was an early career scientist, I would be, and data scientist with that, I would be so excited to jump into this field. And I think that's a good sign that we're on the right track. Thank you.